Decibel scale, very on a very similar note. I mean, you still see a ratio compared to some constant, which we call in this one the threshold of hearing, which is supposed to be the lowest possible audible sound that a human ear can pick up. Very similar to the Richter scale, formula, except I'm doing 10 times a very similar ratio. So, in this case here, suppose that a person's normal speaking voice is 60 decibels. A metal saw produces a sound that is 89 decibels. How many more times louder is the metal saw than a person's usual speaking voice? I mean, again, you look at a difference of 19. You say, okay, well, in many other instances, a difference of 19 is not going to be that big of a difference. However, since that difference is actually indicating a multiple of how many times greater one is the other over the other, we want to try to figure out what that is. So when I look at the voice's intensity level, I'm gonna take that ratio and basically with a decibel reading of 60, you know the intensity of a person's normal speaking voice is 10 to the 6th power times the threshold of hearing. And when I do the same thing for the saw's intensity or loudness, or whichever way you want to describe it, is 10 to the 8.9 power times the threshold of hearing. So I want to say how many more times louder is the metal saw than a person's usual speaking voice. I'm going to do a ratio of the saw over the voice, which is going to be 10 to the 8.9 power over 10 to the 6. The e sub zeros cancel. So, that ratio ends up being 10 to the 2.9 power, which equates to about 794.33. So that saw is about 800 times louder than the speaking voice.